So thank you very much for the introduction and for the invitation. So what I would like to do this afternoon is to try to give you an insight of what is discussed currently at the conference on entropy. So it will not be especially my work, but I will try to give you a more global point of view on this notion of entropy. So this conference actually gathers people from very different communities, so people in statistical physics, because of course this notion first appears in physics. Also people in PDEs, people in probability, and also people in dynamical system. And I will try to show you why probably all these different topics should interact at some point. Okay, so I will try to tell you this as a story, okay? And just enter more technical things just to give some example. Okay, so it's not really a problem if you don't understand precisely these technical things, because this is just an illustration, and I will take time to just summarize the main ideas. And so I hope that everybody will be able to go until the end of the lecture. Okay, so let me first recall where entropy, how entropy is defined. And actually there are a lot of definitions depending on the fields where you are working, on which you are working. So the first, I think the first time entropy appears was in physics quite a long time ago, just to measure the irreversibility of evolution in a physical system, in most physical system. And so this quantity was not, is essentially it's a quantity which is not very well defined, because it's just defined by a lower bound, not really as a quantity itself. And so really what you have to keep in mind is that if you have a transformation which is reversible, then the entropy, the increase of entropy is equal to the heat flux divided by the temperature. So these are really quantities that you can measure, but the entropy is not something that you can really measure. Okay, so it's defined, so this word of entropy is defined by somehow by analogy with energy, but still we will see that it's a very different nature of, because energy has a microscopic interpretation, which is not the case of entropy. Okay, so to go a bit further, I think we need to go to the work by Boltzmann, because he was able to give a microscopic interpretation of this physical entropy just by looking at a very simple system, which is a gas. So here you have to imagine that the gas is just a collection of particles. Okay, and then the entropy is somehow related to the complexity of this description of this gas. So typically what you would like to count is, for a given state that you can observe of your gas, how many microscopic configuration there are. Okay, so there are very simple examples. For instance, if you have only red and blue balls, then essentially you count depending how many configuration with one red ball and 3 blue balls and so on. So this kind of very simple combinatorics that you learn in high school. Okay, so this is really important. And then what Boltzmann was able to do is to see that this microscopic, with this definition, this microscopic definition of entropy, you get the same idea that this entropy, so the complexity, will increase with the evolution. And so just by analogy, somehow he said that it should be the same as the entropy defined by Clausius. Okay, so it's really like, it's not like a proof that it is the same, but more like an analogy. Okay, and then still by analogy, actually entropy has been defined in information theory by Shannon. And you see that it's still something which measures the complexity, because say if you have some information to encode, then what Shannon would like to estimate is, say, the minimal, say, loss of information that you have by transmitting this information. Okay, and so essentially, the way, so this is defined as the average level of surprise of uncertainty if you have a random variable. Okay, so if you have a random variable with low p, then the entropy is defined as the expectation under this p of minus log of p. Okay, so you see that you still have this logarithm, and we will see that it's not just a coincidence. The logarithm is important because this allows to have some subadditivity or additivity property. Okay, so you see that it's still another definition. It has, say, apparently it's not so clear that it's related. It's really more like an analogy. And then there is also the analogy with dynamical system. And actually, I think it's something that was discovered by Kolmogorov and then Sinai, that you can also define an entropy for a dynamical system. So I try to explain how this is related to the previous definition with random variable. So if you have a map T, then on a space X, then you look at the different iteration of this map, and now you, for each X, so for each initial point, you take a partition of your X, okay, and now you just look at the set of this partition where the different iterates are. Okay, so for each X, you define a sequence of labels, okay, which are the number of the set where W1, WK, etc. are. Okay, and then somehow you look at the complexity of this map. Okay, by looking at the so now you see that you still have this mu log of mu, and mu is just a measure of all the x which have exactly the same characterization of the different iterates. Okay, so they have all the points x such that after one iteration you are in xi I1, and then after n iteration you are in xi In. Okay, and you see that if you have a very rigid transform, you see that almost all points in your close to you will have exactly the same trajectory, and then this entropy will be lower than if you have a lot of mixing, and you can have any distribution that you want. Okay, so but you see that here it's important to see that you define a random variable. Okay. And then by analogy with Shannon entropy, you define the entropy for this dynamical system. Okay, so you see that you have a lot of different notions of entropy, and it's not so clear that everybody is really speaking of the same thing. Okay, so I would like to first say that you still have some features which are common to all these definitions. So the first one is that you see that it's really a statistical quantity. It doesn't really make sense to speak of entropy of just a deterministic system with just one configuration and one evolution. Okay, so it's really important to understand that entropy is supposed to, and that's exactly at this point that it's different from energy. Of course, you can measure the energy of just one particle, but it doesn't really make sense to look at the entropy of just one particle. Okay, you really need to have somehow a complex phase space and to be able to measure some kind of complexity. Okay, so it's really a statistical quantity. Now, because of this logarithm, you can check that you have an additive property. Okay, so if you have two independent, so a system consisting of two independent components, then essentially the entropy of the whole system will be just the addition of the entropies of both systems. And so the intuition between this entropy notion is that somehow it measures the level of disorganization or of uncertainty. And you see that that's really related to this second principle of thermodynamics, that you expect this level of disorganization to increase with time. Okay, of course, or the level of information to decrease with time. You lose information at each step. Okay, so that's really important to have this intuition of what entropy is, even though there are different definitions depending on the field, to try to see what you can do with this. So, okay, it's a quantity now. Okay, it's more or less well defined. Okay, and now you would like to know what you can do with this. Okay, is it really an important tool? What can you measure with it? And that will be, say, the purpose of this lecture, to show you 3 different ways of using entropy to look at different problems. Okay, so the first thing that I would like to explain is that because entropy measures the level of disorganization, you have to have, then if you are close to the maximal level of entropy, then you see that essentially you cannot really move very far away, and then you expect to have stability. Okay, so that's the first thing that I would like to show you, is that actually entropy is a very, somehow defines a good distance or a good functional to measure stability close to equilibrium. Okay, so that's the first way you can use entropy to somehow measure some stability properties close to equilibrium. So here I will use 2 examples. I will try to show you 2 examples. Of course, it's a bit technical, and I will not enter all the details of this example, but I think it's important to figure out what, say, on the concrete case, how we can use this entropy. So here, the system I'm interested in is a rarefied gas, which is described by the Boltzmann equation. So let me just explain quickly what it means. So here you see that you have a left-hand side, so forget for the epsilon at the moment. So you have dtf plus v grad xf equals, so imagine that it's just equal to 0. It just tells you that you have particles and that they move, okay, in x. So their position is x, their velocity is v, and they are just moving with straight uniform motion. Okay, so that's just transport. And then you have here a right-hand side, which tells you that actually in a gas, you expect the particles to interact and, say, for instance, to have collisions. And so this Q is supposed to model the effect of these collisions at the statistical level. Okay, of course, you will not describe every collision, but just say that the average effect of collision will be essentially to make the system relax towards equilibrium. Okay, and so now I look at this Boltzmann equation for the gas in a specific regime. Okay, where I'm not very far from equilibrium. You see that this m here is the equilibrium, and I just look at a very small perturbation around this equilibrium, and the size of the perturbation is related to the Mach number. The Mach number is just the ratio between, say, the mean velocity, say the bulk velocity of your gas compared to the thermal velocity, so just the thermal agitation of particles. Okay, so if this number is very small, you see that you expect essentially the gas to behave like almost like a Brownian motion, so you have a lot of diffusion. Okay, and you have still a bit of more ordered motion, which is this motion, and that's this part that I would like to describe. Okay, and here I assume that there is this other number, which is called the Knudsen number, which measure the ratio between the mean free path and the typical length that I'm looking at. And so when this number is small, this means that essentially the particles are a lot of collision, so that you expect that you will be really, really close to equilibrium at each point. Okay, so here you see that you have 2 important scaling. The scaling here, which tells you that the leading order phenomenon is just relaxation towards equilibrium, and then this part here tells you how you will say how the slow dynamics, macroscopic dynamics, will evolve. Okay, so that's what is written here. So because of this penalization on the collision part, what you expect is that your gas is at any point and for any time very close to equilibrium. So this means that if you are close to equilibrium, essentially you know the distribution of velocity of your gas, just by prescribing the local density, the local bulk velocity, and the local temperature. Okay, so instead of having a very complicated distribution of position and velocity for the particles, you know that at each x, you are essentially a Gaussian. Okay, so MF is just a Gaussian, and you see that you have just a few thermodynamic parameters to describe this. Okay, so this means that in order to characterize the motion of this gas, you only need to understand the hydrodynamics, so the evolution of these few parameters, so density, bulk velocity, and temperature. Okay, and in this regime, so what you expect, of course, you need to do a bit of computation, but you expect that this hydrodynamics is non-dissipative in the sense that you will have Euler equation for this flow dynamics, and so you have no. So this means that, say, at the level of, if you project your dynamics on this manifold of just hydrodynamic fields, you expect to have a dynamics which preserve the quantity of information. Okay. Okay, so now what I would like to explain is that in this regime, so since you are really close to equilibrium, at least close to local equilibrium, then you expect entropy to be a very good way to measure the stability of the system. Okay, so the entropy for the Boltzmann equation is just this integral of f log f, as I show you at the beginning. And the nice thing with the Boltzmann equation is that, say, the entropy dissipation now is given by a formula. Okay, it's different from the closed-use principle, where you say, okay, the entropy will increase, but you don't know how much it will be increased. Here, you know that this entropy production is a function of f. Okay, so that's really a major estimate for this Boltzmann equation, which is just the traduction for the Boltzmann equation of the second principle of thermodynamics. Here you have the entropy, here you have a quantity which is non-negative, which is the entropy production, and here you have so the initial. Okay, so it's not really, it's the mathematical entropy which is minus the physical entropy. That's why it's decreasing instead of, okay. Okay, so now what I would like to do is to say that somehow I have very strong stability, and so what we can do is to look at the relative entropy. You see that this is a convex functional, okay, this is f log f, and now what you would like to say that starting from this functional, you would like to construct a kind of metric to say that, okay, now I can really look at the convergence of my system, my previous system, when epsilon is going to 0, just by looking at this relative entropy. And you see that it's just this quantity here now is non-negative, and of course it would be 0 if f was exactly equal to this Maxwellian that I expect to be the right description, the right approximation of my dynamics. Okay, and actually this part here control the L1 distance of between the density and the Maxwellian. Okay, and so here you see that it tells you that you have a method to prove the convergence, which is called the relative entropy method. Okay, so you look at this. So now this is your approximation, what you expect to be the right approximation. F is just the solution of your equation, and now you try to prove that this guy will converge to 0, provided that at time 0 it's almost 0. Okay, and provided, of course, that you satisfy the right equation. And this is exactly what you can do. And you see that this will converge to 0, but this will also converge to 0. And so this means that essentially in this regime, you don't have any dissipation. Okay, the dissipation of entropy is almost 0. Okay, so, and this you really have to understand as the fact that you are very close to equilibrium. Okay, so if you are close to equilibrium, then you are close to the maximal entropy, and so essentially you have no room to have big oscillations. And the other thing which is important is that the flux, so of course this is true only locally, okay, but the flux between the different x essentially is conservative. So essentially you are this is a completely rigid situation where you really expect entropy to control the approximation. Okay, I have another example. Maybe I should be go a bit faster on this second example, but I think it's important because the topic of the conference is about large system of particles. So here now, I don't start from the Boltzmann description, which is already a statistical description of my gas, but really from a description where I just look at all the particles in the gas and try to understand what happens. So here you see that now this function Fn is density over a phase space with n particles, so n position and n velocities. Okay, and I try to write the equation for this Fn. So here you recognize the same transport operator, which tells you that each particle will evolve with velocity vi. And now I just say that what I know is that each time I have two particles, there is an interacting force between the two, which is given by this potential V. Okay, so this is really a very simple example. So if you can think, for instance, of charged particles, which are just interacting via an electric potential, and so you get an equation like this. Okay, and now this is what is called a mean field regime, meaning that you have a lot of particles, but each time you have two particles, you see that the strength of the interaction is very small, of the order of 1 over n, so that in the end, the total force exerted on one particle is of the order of 1. Okay, and so here what you expect in the limit when n is very large is that, so in the previous example, what I was expecting was to be close to a local equilibrium. Here what I expect is to be close to something where all the particles essentially are decorrelated. Okay, so that's what is called chaotic in this field of dynamical system, of statistical physics. So you expect that essentially all particles are independent. Okay, so you expect to be the approximation to be something like this, and now to have a slow. Now, if you project on this manifold of chaotic distribution, you expect to have a slow dynamics. So in the previous example, the slow dynamics was just hydrodynamics. Now the slow dynamics is a kinetic equation, and this kinetic equation is what is called the Vlasov-Poisson equation, which is this equation here, where you recognize here the transport, and here this is just the electric field that you compute as a mean field. Okay? And once again, you are in the case where this equation here is conservative, you have no dissipation. And so you expect this system to be, so the entropy to really be a good way to measure the rigidity of this system, because you are locally close to something which is of maximal entropy, and essentially you have no dissipation because of the slow dynamics. Okay, so if you have these two properties, then you expect the entropy to be a good way of measuring the stability, and that's indeed the case. You can, so once again, you have the entropy, which is this quantity here with where you recognize this Fn log Fn, and then you can define a relative entropy. And so you measure essentially the distance between this Fn and something which is expected to be your approximation, which is maximal entropy, so chaotic here. It's a tensor product. And the F is a solution of the Vlasov-Poisson equation. And then you expect this entropy to control the relaxation and the conversion of the system. And once again, you can prove something like this, which tells you that if you start from an entropy which is, say, controlled, then you will get that this is a good approximation for all times. Okay, so I know that this is of course very rough presentation of these two examples, but what I would like to
I saw the ignorant question. So these kind of results you mentioned, are they straightforward or difficult, or?
No, they are difficult. But I don't want to go into the technical details. What I would like to so what seems important to me in these two examples, and actually a lot of examples on the same kind is that, so what you have to remember from this is that if you are at equilibrium, of course, if you have a global equilibrium, then just the fact that you control the entropy tells you that, okay, you are between the maximum and something which is almost the maximum, so essentially you have no way to move, okay? Now here you see that it's a bit more complicated because, of course, you have inhomogeneities. So essentially you will be close to the maximum of entropy at each point, but of course you can imagine that entropy could circulate between the different points. But here, because the slow dynamics, so the way essentially the inhomogeneities will propagate, because this dynamics is conservative, essentially you have no choice. Okay, so this means that in this case, if you have a relaxation, so if you are close to equilibrium plus the slow dynamics is conservative, then you expect the relative entropy to be a very good way to control the stability. Okay, so that's the only thing that you should remember at this stage. There is a first class of examples where you have problems in which the approximation is local equilibrium plus the flux are conservative, and then entropy is a good way to control the stability. Okay, so that's the idea behind this first part. Now, what I would like to do is to look at examples where I start further from equilibrium, because of course life is not always at equilibrium. Okay, and so I will start again with a first example on the Boltzmann equation. So now I don't have any scales, particular scales or particular scale separation. I just have this Boltzmann equation with two parts, the transport and the collision. Okay, and I just assume that at time 0 I have a finite entropy, but okay, it's finite, but could increase. It's not really a problem. Okay, so now I try to explain what we expect in this situation. So we know that these collisions, what they do is that locally they push the system towards local equilibrium. Okay, but this is just something which is local in X. Okay, but of course you have the competition of this mechanism with another mechanism, which is the transport, which try to homogenize the macroscopic fields. Okay, and so you have two things. You have one thing which tells you that locally the distribution would like to be a Maxwellian in V, and another phenomenon, which is the transport, which tells you that you would like to have the same density everywhere, you would like to have the same bulk velocity everywhere, and so on. Okay, so you have this competition between two mechanisms. And what you would like to prove is that because of this competition, what you will do is to relax towards a global equilibrium, where of course you are Maxwellian, but the moments are the same everywhere. Okay, so that's what you expect. And actually you even expect that it should be like an exponential relaxation or something really a strong relaxation. Okay, and so actually you can do something like this, but now you don't need only the entropy, you also need to understand the entropy production or entropy production. Okay, and so now you see that it will be another field of mathematics, because it really relies very importantly on functional inequalities. Okay, so that's a different field. So here what you expect for the Boltzmann equation, so what you would like to have, actually is wrong, but it's almost true, is that the entropy production actually control not the entropy, but the distance and actually the relative entropy between your distribution and the projection on the local equilibrium. Okay, so and actually it was Ciaccinani's conjecture that the entropy dissipation really control the distance between the local equilibrium and your distribution. So it's not true, okay, but it's true provided that you add some technical assumption. Okay, I will not enter this. And now, once you have this, you see that because of this functional inequality, if you combine this with more an argument of ODEs, essentially, you can prove that you can describe this, what is called this hypocoercive mechanism, because you see that if you forget about the inhomogeneities in X, you see that now you have your relative entropy, which tells you how far you are from equilibrium. but at the same time, you have a dissipation, which is essentially like the relative entropy. And so you see that you have an equation like dt h plus h is equal to 0. And so you know that this will give you the exponential relaxation. Okay? But now it's not true, because you see that you have two different kind of equilibrium. You have the global one and the local one. And so you have to combine these two mechanisms with the transport and the relaxation. And so you end up with a system of like this. So you see that if you look at the time derivative of the relative entropy with respect to the global equilibrium, then it's something like it's bounded from below by the relative entropy with respect to the local equilibrium. And you have at the same time another equation which tells you how the transports act on all of this. And you have now a second derivative with respect to time of this relative local relative entropy, which is controlled by one from below by these two things. Okay, so this is not completely correct, but okay, you can. It's essentially the proof of De Villet and Villani that for the Boltzmann equation under additional assumption, you have relaxation towards global equilibrium, and that it's almost, it's not, but it's almost exponential. It's faster than any power. Okay, and so I would like to discuss also a little bit the second example, where now I have, as in my first example, problem with different scales. So I have the Boltzmann equation, but I have separation of scale, which tells me that essentially my bulk velocity, once again, is very small compared to the thermal velocity, and that I have fast relaxation. Okay, so if I have fast relaxation, of course, the transport is much slower than the relaxation. So really, what you see is local equilibrium almost everywhere. But now these two parameters are the same side. Okay, so it's almost like the first example, but we will see that it's not exactly the same thing. So the first thing which is the same is that you are close to local equilibrium. Okay, so you are locally like a Maxwellian, just because this is the leading order term in the evolution. Okay, so I have relaxation towards local equilibrium. Okay, now I also expect that because of the transport, I will have a slow dynamics, a slow hydrodynamics, telling me something about the bulk velocity, the temperature, and the density. But now this slow dynamics will not be the Euler equation, which is conservative, but the Navier-Stokes equation, for which you have a diffusion term. Okay, and this the reason why you have this is that you have a much more complicated interaction, and this is in the same spirit as the hypocoercive mechanism that I presented just before. So you have a kind of coupling between the relaxation and the transport. Okay, so because of this scaling, in this specific scaling, the relaxation is fast, but it's not so fast, and so you still say, when you look at the hydrodynamics, you still see something from this relaxation. Okay, and so this is very different, because now the Navier-Stokes equation, contrary to the Euler equation, it's not conservative. Okay, and so this is not true that you can say that essentially you have the very strong stability, because now you see that you have a little bit of more room to do something different. You have a little bit more dissipation. You still have dissipation at the level of the macroscopic dynamics. Okay, so I will not explain. So this is how you can compute this hypocoercive mechanism. Actually, you prove that you are close to the equilibrium, but you have a small correction here, and then you can compute this small correction and see that it will generate second-order term in the equation. Okay, so I will not explain this. It's much too technical. But one thing which is important here is that this means somehow that in order to see something, so you see that to look at the relaxation, the global relaxation for the Boltzmann equation, we needed the functional inequality between the entropy and the entropy production. Okay, and now if I would like to look at this kind of convergence, this means that I also have to work on the entropy production. Okay, in my first part, everything was conservative, so I didn't care about the entropy production. now I have to take care about entropy production. And so if I would like to have a method of modulated entropy, I need both to modulate the entropy and the entropy production. Okay, and that's really important. Okay, I will not spend too much time on this because I would like to have time also to summarize this. So you see that here we are in a slightly different case than the previous part. So I still have a very fast relaxation mechanism. So I still expect to be close to some equilibrium, and that the relaxation to go to this equilibrium is something which is like exponential or something like this. Okay. But now the difference is that when I project on a slow manifold, I get something which is different because it's not conservative. Okay, so that's the case of the Boltzmann, the Navier-Stokes equation. But it's also the case if I have this just a relaxation for the Boltzmann equation. I have these two mechanisms which are say relaxation towards equilibrium and kind of oscillations around this manifold which are due to the transport. Okay, so now I have two mechanisms, and one is okay is somehow faster than the other, but not fast enough in order that you can really decouple completely the two things. Okay, so now I still have kind of I remember that say even on the slow part, I still have a bit of dissipation. Okay, but okay, if instead of just looking at considering the entropy, you work both with the entropy and the entropy production, you still can do something. Okay, and you still have okay. The conclusion is the same: is that you have stability. Okay, you need to work both on the entropy and the entropy production, but in the end, what you have is that you can still you have a very rigid kind of rigidity result where you control everything, and then you can prove that what you expect is just happening. Okay, and so now I will go to the last part of the talk, which is the case where you are really out of equilibrium. Okay, so the first part was really close to equilibrium, then it's fine. You control everything with entropy. The second part was, okay, you are close to equilibrium. There is a little bit of dissipation, but okay, if you just combine entropy and entropy production, then you are still safe. And now the last part is you are really out of equilibrium, and then it's not clear. Okay, so I would like to look at two different examples once again. Okay, so the first one is still a system of particles as in the first part, except that we will look at a different scaling. Okay, so here I just look at what you can imagine as a gas, a neutral gas. So you have particles which are just small balls at spheres, and now they are really, really small. Okay, but there are a lot of them. And what you expect is that, okay, they move around, but sometimes they have a collision, and you expect typically that each of these particles will have one collision per unit of time. Okay, so that's what is called a low density regime. Okay, so in order to have this low density regime, you assume that the size of the particles is epsilon, and that you have a scaling relation between the number of particles and their size, in order that, okay, it's a computation which is due to Maxwell, in order that, say, in average, you have one collision per unit of time. Okay, and I start, as in the previous example, with something which has maximal entropy, in the sense that I have, okay, I have a tensor product. All the particles are independent, so essentially I have, say, the complexity is already maximal. Okay, so I start with this. Okay, but we will see that in this regime, this is not true. That this is not really true. That it's a very good approximation. Okay, so in the mean field regime, what I said is that if I start with a system of particles in mean field regime, I start with a chaotic distribution, then I expect that I have this combination of being really close to a chaotic, so tensorized product, and because the slow dynamics is conservative, then it's a good approximation essentially for all times. Okay, now it's not true that it will be, so it's not true that the Fn will be close to the tensor product. It's true only in a weak sense. That's meaning that I cannot look at Fn, but I can just look at finite marginal of this Fn. Okay, so I fix k, and will go to infinity, and what is expected to be true, and what is actually true, at least for small times, is that if you project, so you look at a finite projection, your Fn lives in a phase space which is 2ND dimensional, but now this is just in a phase space. You just look at the correlation between k particles. Okay, this is a k particle correlation function, and this will be close to something which is a product. Okay, but this is not true that you can take k to be n. Okay, you really have to project on a finite dimensional space. Okay, so that's what I mean by weakly chaotic. It means that Fn is not close to F tensorized to the n, but what is true is that if you project on a finite dimensional space, then it's true that you are close to the tensor product here. Okay, and so and we will see that it's not true that you are that so everything here has to be understood in a weak sense. Okay, so it's really different. It's not a very strong relaxation which is controlled by the entropy, because you don't have choice. You are essentially completely blocked by the fact that you have to be close to the maximal entropy. And now if you look at the slow dynamics, so the projection, so the slow dynamics is just the dynamics on this one-dimensional projection, which is just one F. Then you get the Boltzmann equation, and the Boltzmann equation, so we saw it a lot of times. You see that it's very different from the Radov equation. The Radov equation is completely reversible, it's conservative, everything is conserved. For the Boltzmann equation, it's not the same. The equation itself encodes irreversibility and the fact that somehow part of the information is lost. Okay, so you see here it's very different from the mean field, the mean field regime. In the mean field regime, maybe it's something that I can try to summarize here. So in mean field, and now I have low density. So essentially, at the very beginning, you see that you have a system of n particles. It's almost the same. Okay. Only the scaling of the interaction is different. So mean field means that you interact with all particles, but each interaction is small. Okay, so interaction with all particles. But each one is small. While here in the low density, essentially you see 1 particles per unit of time, so you have just a few interactions. But you see that it's in terms of stability, this is much better, because if you change just 1 particle, it will not change anything. Of course, if you change 1 particle here, since you just see 1 particle, of course, it's a dramatic change. Okay, so you expect this system to be much more stable than this one. Okay, and so you see that the result is that here what you expect is that it's strongly chaotic, in the sense that you can look at all the particles and you really have something which looks like this. Okay, the distribution, the good approximation, plus the fact that F, the equation for F is conservative. Okay, while here it's just weakly chaotic, so it means that this is not true. Okay, this is like Fn, so this is not true. The only thing which is true is that if you project on a finite dimensional space, you get the same, but you need the projection. You cannot. So this is like the projection here. Okay, and the equation for F is not conservative. Okay, so the situation is much worse. And so you see that essentially you lose a lot of information. You lose information here because you see that if you look at the information which is encoded in F, and so in any product here, is smaller, strictly smaller than the total information that you had at the beginning. Okay, so something is lost, and this something is lost in these very small scales. Okay, so this system here is very robust, very stable, and we expect, and actually you can prove that it's stable in the sense that you have really entropic convergence. So the difference between these two things is small in relative entropy, while here it's not. It's just completely wrong. It's not possible because if you start for the system of particles, the entropy is conserved. And if you look at the entropy which corresponds to the transfer product here, the entropy is not. Okay, so there is by no means they can be close to each other because one is strictly smaller than the other one. Okay, so I think it's really important. And the reason why you have no stability is that, so actually no strong stability is that you see that when you have these very small particles, if you just change a little bit one of the particles, then you will completely change the trajectory of everything. Okay, so it's not true. So you have a lot of instability at the microscopic level, and then instead of being able to really follow each trajectory, then the only thing that you can expect is to have a good approximation of what happens, say, in average or in probability. So you see that somehow what is wrong is that you have a kind of deterministic rigidity. The only thing that you can expect is something which is much weaker, which is something in average or something in probability. So it's really different. And by doing this, you lose a part of the information. Okay? And so that's really important, is that this mechanism that you have a microscopic uncertainty, which is due to this instability, and now it's transferred in some macroscopic randomness. When you write the Boltzmann equation, actually you write, so this Q of F that I never detailed is a collision kernel, where essentially it's like a jump process in the phase space. And so you see that, say, it's really intrinsic in this equation that you have a kind of randomness. Okay, and so the problem is that say, right now, we don't have any suitable functional framework to try to encode this weak stability. Okay, so for the others, just playing with the entropy or playing with the entropy and the entropy dissipation production, then you can have some stability. But here, this is a very weak stability, and then you don't know what to do with this. And so before I stop, I would like to show you one example in dynamical systems. So I'm not a specialist of this, but I think it's interesting because I think it's related to this. And where you have the same kind of microscopic instability, which is transferred to some randomness. And I think it would be great to be able to find a functional framework, or maybe to understand how entropy can help to encode all these things. So here, this is, so I will not explain why it's a bit like the same, but okay, I will just tell you what is this model. So here, it's a complicated, so it's a model where you have a lot of different scales. So you can imagine that you have exactly the same for your system of particles, just looking at scale epsilon, epsilon square, and so on. Okay, so here you have a lot of scales, which are here. And now you have a dynamics, which is given here. So here, A is just a Arnold scat map, which is given here. And so you see that you can compute the value of your process at each point here, depending on these two values here. Okay, so you have compute this point with these 2 points, you compute this point with these 2, etc. Okay, so that's the representation of these dynamics. So say the elementary object is something which is very, very well known from by, say, in dynamical system, this guy here. And what is very important in this system is that it has very strong mixing properties. Okay, and so of course it's very complicated to define this system with an infinite number of scales. So you start by just keeping only a finite number of them. Okay, and at the lower level here, so at the smallest scale, you just prescribe that. So you say, okay, it's very small scale, so I don't know exactly what happens at initial data at the initial time, and so I just replace this by a random field. Okay, so this is a dynamical system. Everything here is prescribed except the lower level here where you put some randomness. Okay, and now of course what you would like to understand is whether there is a limit for this system. So can you just remove this cutoff and just now look at an infinite number of scales. Okay, and so what you can prove is something which looks like a bit like the Boltzmann equation, because in the end, in the equation, you get something which is random at any scale, including the macroscopic scale here. Okay, so this means that somehow all the details, all the very small scales here, so you see that at the beginning there is no randomness, but somehow the randomness will just emerge from the very small scales. And that's exactly what happens with the Boltzmann equation. The randomness just comes from the fact that you have all these very unstable collisions, and at some point this is. Okay, so what you can prove is that this system is not rigid. You don't have this kind of very strong relaxation as in the first two parts of the lecture, in the sense that there is no deterministic limit. So if you start with one, say you prescribe all the initial data up to the cutoff scale without any randomness, then you can converge towards a lot of different things. Okay, so there is no limit for this system, because depending on the way you somehow regularize the system, you can get a lot of different things. Okay, but if you add a little bit of randomness really at the very small scale, then you see that the system, of course, will have a lot of solution, but actually the distribution of all this solution is something which is intrinsic. It doesn't depend on the law of the random variable at the very small scale. Okay, so here, I think it's really nice. It's an example to illustrate what physicists call spontaneous stochasticity, meaning that somehow in your system, you don't expect to have a lot of rigidity. You expect to have really a lot of flexibility, and the way, say, it's not a good idea to try to prove some uniqueness or some strong convergence or some stability, because actually you don't have. What you expect is that you will have a lot of different possibilities, but the distribution of all these possibilities is something which is robust. Okay, so I think it's a very, very nice example. But the only problem is that in this example, essentially you compute everything because you can use Fourier transform, and then everything, all the computations are explicit. So essentially, this doesn't give you any mathematical tool to deal with this kind of problem. Okay, so it's a very nice example because it really explains how you can have a system where at the microscopic level everything is unstable, and nevertheless at the macroscopic scale you get something which is very stable. Okay, but you see that in mathematics we don't have so many, so actually I know none of them, so many tools which allow to prove a lot of stability if at the macroscopic scale everything is very unstable. Okay, so I think it's really a nice example, because here you really see this, everything is really mixing, but still at the macroscopic level you see something which is very nice, that you can really but you see that here you don't have any mathematical tool or any mathematical strategy to look at more general system in this direction. Okay, so I think it's a very important problem, because I think it's the thing that is missing to understand this Boltzmann grad limit here, and the thing which is missing to understand is also a lot of things in turbulence and so on. And so there is a question whether entropy can be a good tool to say something in this direction. I'm not so sure, but if anybody has any idea, I think it would be great. Okay, I will stop here, and thank you very much for your attention.